Okay, so today I wanted to talk about the step function in maths, but not derived the typical way through Fourier series. In fact, we will derive it without Fourier series at all, and then compare it to the Fourier series example. So here we do have the Fourier series example. This is by definition the step function, but it's a little bit altered. I've altered it such that the amplitude, the height of the step function is 1 over L, and I'll describe what L is in a minute. And its length of one like oscillation or half an oscillation is L. So consider the potential well problem from introductory quantum mechanics. You have a set integer number of wavelengths within an infinite potential well, and that corresponds to a probability of finding a particle associated with that wave function in that potential well at any given point. Now, you can arrive at the classical intuition behind such a problem by taking the quantum number n to infinity in any situation. So in this example of potential well, n corresponds to the amount of wavelengths present in the potential well, and at that point when it's infinite, you can, well, that would be the classical example, and that corresponds to a uniform probability of finding a particle within that well. You could think of it as such: if you had a one-dimensional well in real life, a real well with walls, and you had a classical particle bouncing back and forth in there, if you didn't know that particle's starting position, you would have a 1 over the length of the box probability of finding it at any point. And here we've done the same thing with the step function. So the height is going to be 1 over L, and it's going to be L long, right? But we'll arrive back at this in a minute. So I want to consider a summation of wave functions. I want to consider, so we have the probability, like amplitude of the wave function is the modulus squared. So that's going to be, I'm assuming you'll know that the wave function phi of x in this case is 2 over L sine n pi x over L, right? And you take the modulus and square it. So we arrive at 2 over L sine squared n pi x over L. Now, if I simply just sum these up, then I should, to infinity, from n equals 1 to infinity, I should arrive at something that looks a lot like a wave, a square wave, right? So n equals 1 to infinity. But of course, because I'm adding these together, it's going to get bigger and bigger and bigger. So it's going to get bigger by, well, actually, I won't say infinity because that's going to make it difficult. I'll just say the letter n. It's going to become taller by m times. So if I just divide it through by m, then this should look very much like a square wave, the classical probability of finding a classical particle in a box, which should just be a square like this, right? Where the height is 1 over L and the length is L. Now this also should look the same as this, but they're not the same, right? So I guess I'll put a screenshot up of the comparison of these. They won't be exactly the same. The difference will be in the phase, right? Because we know that sine squared is not in phase with sine. And that'll be the only difference. But when m goes to infinity, by definition, because this is the step function, then they will be the same thing. Like functionally, the phase won't matter because they'll just be flat at infinity. So yeah, I mean, it's really cool defining the step function through quantum mechanics alone without considering the Fourier series, a mathematical construct. So yeah, just a quick one. I also wanted to note something quite interesting about this and how this corresponds to a greater picture of quantum mechanics. Because you could just take the wave function as it is and take n to be infinity without doing any summation, and you would still have a wave function that I presume peaks at like probability amplitude of 1 over L. But in that case, it's not quite satisfactory because it oscillates up and down still, so there'll still be points where there's no chance of finding it. So one could perhaps link this summation idea back to the concept of path integrals in Feynman's depiction of quantum mechanics. Not that I'm in total agreement with how he views things, but because we're summing up different wave functions, it's like whatever this classical object is taken every single possible path throughout this well, and the summation of those paths up at different energy levels gives us what we intuitively expect the path to be. And that's just the square like wave probability of finding it at any point, which is just intuitive. So, I mean, I would try and visualize this for you, but I'm not very good at technology, so I don't think I could create anything that looks cool enough to give you a good idea of it. But I would implore you to search or do some research on path integrals and Feynman's, interpretation of that part of quantum mechanics. It's quite a good video about it that was popular recently. I'm not quite sure what it's called, but yeah.